Hey there, welcome in. I'm Kirk Harnack, Vice President of Telos Systems. And this is the webinar that we have given to quite a few people. This is in a video format that I'm doing just for you. Okay, if you want to believe that. Just for you. I am going to breeze through this webinar pretty quickly. Thanks to this being on video, you can easily just back up a little bit if there's something you missed and head over it again. Hey, I wish I had some variety for you, but you're going to be hearing me for about the next 35 to 45 minutes. So put on your thinking caps and let's get going. The title of the webinar is IP Audio Integrity, 3 Keys to Great Audio Over the Public Internet. I got to tell you, we're kind of in this, I'm going to say this bad old time of IP audio. There are a lot of standards running around. There's a lot of non-interoperability among different brands, but there is also some light at the end of the tunnel. There is some interoperability. There are plenty of people who are using IP audio, even over the public internet, for 24/7 studio transmitter links, even for HD video. Yeah, CBS Sports is using the public internet to ingest HD video from some remote sites. So let's get right into it and discover about IP audio and what you can do to make it better. Let's cover a few things first. Oh, this poor guy. Look, he's got his head in his hands. He just discovered he's going to have to install some IP audio gear. And like many engineers, like myself, there's a lot of fear and doubt and discomfort about IP audio. Let me remind you, though, that right now there are over 4,000 studios around the world using IP audio within the controlled environment of a broadcast studio. We're talking about, routers and switches and wiring that's all under the control of the station engineer. For those guys, for those stations, doubt is gone. IP audio really is everywhere. But what about when we go outside? What about when we want to take our audio ingest or distribution outside of the walls of our broadcast facility? Well, for years, for even decades, we've used tariffed services from phone providers like ISDN, T1, and E1 services. These services, in most locales where they're offered, they're guaranteed to work. They have to. If the phone company offers it, it has to work. And that's always been a point of comfort for the engineer. But, maybe you haven't thought about it this way. It's also been a point of disappointment because if it doesn't work, there's nothing you can do about it except call the phone company. And if the performance of it isn't as much as you'd like, let's say you want more than 128 kilobits per second from an ISDN link, well, you can't get it. It works the same now as it did 20 years ago. Also, as engineers, we've dealt with RF links for years and years, typically analog 950 megahertz or digital at the 950 band, and some other frequencies in other countries as well. Well, nowadays we're looking at dealing more with IP links, both private IP links that the bandwidth is all yours. Well, there may be a cloud somewhere, but you're not aware of it. As far as you know, it's all yours. And dedicated IP links, and also the public internet. And that's what this session, this webinar, is mostly about, the public internet. Here are a few codecs, IP codecs from different manufacturers. These all work just fine to get audio from here to there, typically stereo audio from here to there. They have different levels of sophistication and different choices in the features that you may need. I do want to point out that there literally are thousands of IP codecs in use daily by broadcasters. They are connected to each other via public internet, by private WAN, even by IP radios, which is a pretty interesting solution there. Many of these, most of these are working absolutely perfectly. But there are some that could use some optimization. So that's what we're going to talk about here, how to optimize this kind of thing. Now think for a minute about a service that works pretty well, and that would be Netflix. It's terrifically popular. Here at my house, at the Harnack house, we use Netflix a lot. For $9 a month, my 2-year-old kid gets to watch all kinds of TV shows, and we get to watch, movies and such. And it works pretty reliably. Think about it, Netflix is pretty much one way, from their servers to your tablet or television or iPhone or other device. There's a little bit of feedback in terms of, hey, I need a lower bit rate, or hey, I could stand a higher bit rate. There's also the notion that it's not really real time. It's buffered. There's a lot of buffering going on in your device. But I bring Netflix up as an example because it is a service that is regarded to work very reliably. And it works reliably in part, to a large part, because it doesn't need to be real time. It doesn't need to be low latency. You don't realize that the Netflix server pushed the movie out to you a good 20 seconds before you're watching it. So you've got whatever it is, 10, 20, 30, 40 seconds worth of video buffered up in your player at all times. Well, there's another use for the public internet, and I use the example of CBS Sports. CBS Sports has the ability to go out and do HD video, 3-camera, live shoots, live interviews out in the field, and they don't have to roll a satellite truck to do that. They make arrangements for good internet access from a hotel or whatever venue they're at, and they use some good compression technology to compress that 1080i HD video down to a few megabits per second. And they send that over the public internet to New York, and they do it in a fairly low latency mode. This is working very well for CBS and for other television networks. And I just bring that up as an example because I've heard some people say, well, I wouldn't trust the public internet for my radio audio. Really? You wouldn't? Well, maybe there's some things you need to learn about how to make IP audio reliable. And, well, that's why we're all here, right? Let me show you an example here of a radio station in Florida. This is in Sarasota, Florida, the Joy FM. And right there's a fellow named Avery Ditmars and his friend Dave Anderson. Avery's the regular engineer there. Dave is the consulting engineer. And I got to admit, Dave Anderson is kind of an IT guru. He's pretty sharp at this stuff. They're using the public internet, connected to it by several different means, to transmit all of their full-time, 24-hour-a-day studio transmitter link audio. The zip ones, the Telos zip ones they have are their full-time STLs over the public internet. Now, let me show you how they're doing this. At each location, both at the studio, at the main studio, and at each of 5 transmitter locations and 2 extra studios, they have a sophisticated router, a router that they can establish VPN links over, that has multiple WAN interfaces, so a reasonably sophisticated router. Good news is they're not expensive. They happen to be using MikroTik brand router board routers, and these are pretty exciting piece of equipment. You can use Cisco or other brands, but these ones from Routerboard are pretty sophisticated, and the price is definitely right on those things. Then to connect to the public internet, at the main studio, they actually have 4 different internet connections. Cable, DSL, they have a WiMAX feed from an outside antenna, and I forgot to mention on here, they also have Fios coming in, fiber coming in. And so each of these connections to the internet goes to their router board router. So they have all these different possibilities, 4 different possibilities for connecting to the public internet. At each transmitter site, they have taken the trouble to make sure each site has at least 2 sources of internet. Now, those sources are typically cable modem, or DSL from the phone company. But at a few sites that are rather challenging, they have 4G LTE as an over-the-air wireless backup option, or they get internet nearby, maybe a few miles away, and then use an inexpensive RF IP link to connect the remote transmitter site to where that internet is there and reliable. So at each transmitter site, they have typically 2 sources of internet. And then each of these routers connects to various Telos Zip 1s. They have elected to make the job easier on the Telos Zip 1 by establishing virtual private network routes, VPN routes, from each transmitter site back to the main studio. And they make a separate VPN over each path, and they have the ability to have the router switch paths if needed. If one path goes completely down, they just switch to the other one. The router does that automatically and switches back when the other VPN is up and available. Using this method, they have a very consistent site-to-site setup, and they have excellent reliability, at least as what's the kind of reliability that you'd get with an RF STL, given atmospheric inversions and things like that from time to time. So great reliability. Typically at each of these sites, they're running AAC algorithm at 320 kilobits per second. So the audio is just pristine at each of these sites. And by the way, the Zip 1 can also do uncompressed linear audio. So if you've got about 2 megabits per second, that's very reliable. You can use PCM as, or pulse code modulation, what we used to say linear, between sites. They have a couple of sites that are challenging, and occasionally the bit rate does go down. They have one site where they can switch automatically from AAC down to HE, or high efficiency AAC. And the Zip 1 does this automatically. It is nearly inaudible, just a small glitch when it switches. And it doesn't hunt back and forth. You know, it's one or the other, and then when the bandwidth becomes available again, it switches back to the AAC. Let's look at another situation. This is Dave Barnett with KVMR-FM in California. And Dave is the engineer for a community radio station that does a lot of music remotes. So at the studio, they have a Zip 1 and a connection to the public internet. Well, they have a terrific 2-day musical affair that they broadcast every year, in addition to all their other musical broadcasts they do. And it's out in the middle of nowhere. They have a hard time getting any connectivity out there, but they do have some mobile connectivity via an old WiMAX system that they're able to pick up on. So the WiMAX system is connected to the public internet, and they use a special modem, a WiMAX modem, to bring that WiMAX internet into their remote setup. And this is pretty reliable, although the latency and jitter, I should say the jitter, is reasonably high, and occasionally there's lost packets. So at the receive end at the studio, they actually dialed in more buffering, anywhere between 3 and 5 seconds of buffering. Now, that's way too much to do a live back-and-forth talk show. But to bring this music remote, which is going on all day long, it's entirely acceptable to bring the audio back that way, even if there is a 5-second buffer at the studio end. But remember, it's very challenging at the remote end. So that's why they've added that buffer. Let's look at one more place, and that is, hey, I just shot this picture last Friday here in Nashville. This is a remote done by Lightning 100, WRLT. And say hello to Josh here, Josh Livingston. He's he's the promotions guy, but he's also the remote tech, although I'm told that he's really not very technical. Great guy, though. Hi there, Josh. He's wearing a Tennessee Titans hat, so he's a big fan. But he's holding a WiMAX modem. Now, this one is a product from Clearwire or Clear, and if you got a good signal, it gives you good internet. Certainly enough to do one of these broadcasts with. So also at the broadcast, they bring along a Telos Zip 1. There it is. And they bring along a router, just a standard off-the-shelf Netgear router. It's been configured to prioritize the audio packets coming out of the Zip 1. They also have a laptop there on site, and you can see there a fellow named Wells Adams. He's the afternoon talent on Lightning 100. And so he uses that laptop connected through the router and to the WiMAX. He uses that to control the automation system back at the radio station. Of course, the same connection, the same router and WiMAX modem also take his voice, low delay, AAC enhanced low delay, from the remote site. Here we are at the Soulshine Pizza Kitchen on a Friday afternoon in Nashville, and they draw a large crowd there at Soulshine. So there you can see a little close-up of the Zip 1 and the WiMAX modem. So, works well for remotes, works well for studio transmitter links. Maybe there's more applications you can think of. So here are the 3 keys to getting great audio over the public internet. Number 1, your internet connection. You know, folks, we got to at least have something to transmit this audio over. And it's important to whenever you want to consider using a given internet connection to transmit live, low delay, high quality audio, you need to characterize that connection. You need to find out how it's working. And we're going to give you some tools to do that. You also need to optimize that connection. Hey, is there something we can do to make it better? Like, if there's some people using a BitTorrent client on other computers, maybe we need to ask them not to do that, since BitTorrent ends up getting a whole lot of pings from the outside world. We need to configure and optimize each router that is in the system. Now, each of them that you have control over. So certainly at the radio station, and hopefully at the remote side too, you can optimize those routers. And then you want to choose the appropriate IP codec mode, the algorithm, the bit rate, and the buffer size. Some of those things can be done automatically for you, at least with a Telos Zephyr Zip 1. All right, let's check out the first one now, and that is your internet connection, characterizing that and optimizing it if we possibly can. You know, there's an alphabet soup of abbreviations here. Some of these we probably should be familiar with, so I'm going to cover these briefly for you. Feel welcome to look some of these up. TCP/IP. Well, we've heard that. What does it mean? Transmission Control Protocol, Internet Protocol. And TCP/IP is what we normally use for web browsing, for getting an email, for transferring files, things like that. TCP/IP is just that, a transmission control protocol. It makes sure that we transfer from a server to a client or from one computer to another. We transfer every bit and byte of data accurately. TCP/IP is for when time doesn't matter, but accuracy does. Obviously, it's not very good for live audio, but it is good for lots of other stuff. UDP is the protocol. What is it? User datagram protocol. And, a bunch of $3 words there, but basically UDP means I'm going to send you data because I know it's important that you get it in a timely fashion. I'm not going to check on whether you actually got it or not, and you're not going to tell me. You're just going to do the best you can with the data that you receive. I'm going to send it all. The internet may lose a packet or 2 or 10, and you're going to do the best you can with what you get. UDP is what we use for all kinds of things like voice over IP telephony. UDP is for anything where accuracy doesn't matter a whole lot, but time sure does. We can't afford to get anything late, otherwise we'll get dead air, and we don't want that. RTP, real-time protocol, that just means we have timestamps to play back audio or video at the proper time in a timely manner at the correct speed. Jitter, well, this means how much variation is there in the arrival time of one packet versus another, assuming that they've been sent on a regular basis. So if we send a packet, and we receive them as a packet, that would be a lot of jitter, and that's what we don't want. Buffer, we use buffers to overcome lots of jitter. If there's no jitter at all, we don't need a buffer. We can use each packet just as it arrives and everything's hunky-dory. If you're in a controlled environment, like an Axia IP audio network in your studio, that's exactly what we do. But if you're in an environment where you don't have control over the jitter, because you don't have control over the end-to-end connection, then we do need to buffer some audio, buffer some packets. There's 3G, 4G, LTE, and WiMAX, just different technologies for connecting devices with typically the phone company or whatever your phone provider is. But all these can carry data. There's coding delay. That's the delay that we get by taking linear audio and compressing it using one of the compression algorithms like MPEG Layer 2 or MP3 or AAC or one of the AAC variations or aptX or enhanced aptX. There's delays there. And different algorithms offer different amounts of delay. Then there's also the whole idea of latency. Latency is a combination, latency or delay is a combination of the delay it takes to code the audio, well, and to decode it at the other end. The delay it takes to packetize the audio or unpacketize it, and that packet's delay in getting through the internet or whatever devices it has to go through. And then there's buffer latency or buffer delay. How much do we choose to delay in order to make our system more reliable? So, now that we know all that, let me tell you how to guarantee perfect IP audio every time. Guaranteed. You'll never have a problem. Here's how you do it. Plain and simple. Use a perfect IP network. Duh. Yes, I'm feeling rather smug now that I've told you that. That's the gist of the whole thing. You can go home now. Well, okay, maybe not. We still have to deal with the internet. If you use a perfect IP network, then all of this stuff that we build around IP codecs doesn't matter so much. You send packets from a dumb IP codec and you receive them on a dumb IP codec, and everything's just hunky-dory, and there's unicorns and rainbows and the sky is blue and it's just terrific. All the trouble that we go to with IP codecs are to overcome imperfections in the network. Like this. Is this how your yard looks? Not like that. Not like the pretty one. Yeah. That's what we got to travel. That's what our packets have to travel through. And maybe you have firewalls to deal with. And who knows, maybe you have sprinklers to deal with. Well, we're going to help you work through. All right. One technique for getting reliable audio from point A to point B, and you probably wouldn't do this with a broadcast remote, but you would do this with infrastructure, and that is to send the same data twice. Now, that's a valid technique. Now, to do this, you don't want to send it twice through the same provider. This would assume that you have two providers, two internet service providers at one location and at the other location. And it also assumes that these providers, hopefully, have two different internet backbone providers, for the ultimate in reliability. Very helpful technology, and Telos has a product that does this right now. But that's not what we're going to be spending most of our time with right now, because at many locations, when you go out and do a remote, you don't necessarily have two providers available, and you don't necessarily at the receiving end either have two providers available. Could, but you may not. Another technique to help improve reliability is to send two streams, perhaps even over the same provider, but to offset them in time, so that you're sending one stream and then you're sending the same stream a few milliseconds, or maybe some tens of milliseconds, or maybe 100 milliseconds later. And that way, if there's a packet dropped from the first stream, well, hopefully the same packet in the second stream will get there. So a perfectly valid technique. It can work if you only have one provider, but you have plenty of bandwidth. Let's say that you have that. You have only one provider available to you at one end or the other, but you got a lot of bandwidth. Well, you can send the same stream twice, offset in time, and have a chance of recovering every packet at the other end. Now, this doesn't help at all, of course, if that one provider you have just totally takes a hit and goes off. Then you're kind of out of luck there. Well, the Telos iPort is a product that actually has 8 IP codecs in it. Now, these IP codecs that are in the iPort aren't really smart like the codec that's in the ZIP1, the Telos ZIP1. But there are 8 of them in there, and they do a variety of different algorithms like MP3 and AAC, MPEG Layer 2, couple different flavors of AAC as well as linear, and optionally, this can do enhanced aptX. But the assumption is here that you're in a real infrastructure setting, that this is connecting places that are meant to be connected pretty much permanently. And you've gone to the trouble of setting up the IP link such that it's going to be there and be reliable. The Telos iPort is intended for private networks or networks where you do have control over the quality of service. Not necessarily meant for the public internet, although there are people using it on the public internet as well. Especially now that the iPort offers dual pathing. You can choose 2 of the 3 paths here and have a very good chance of always getting the packet that you want. Even if there's a packet missing from the satellite link or from the microwave link or WAN or from the public internet, packets drop, they probably have made it from the other path. So that's the Telos iPort. Here, though, is a screenshot of the Telos ZIP1. And there's another ZIP1. And they're going to connect to each other this way. We're going to push packets, IP audio packets from one to the other. And we're going to receive packets back from the far end to the near end. Telos has added something else interesting to this mix, though. It's called Agile Connection Technology. We designed the ZIP1 on the assumption that you're probably going to have just one internet connection available to you. We want to use that internet connection as efficiently as we can. We want to give you the best bit rate possible, so you've got the highest possible audio quality. At the same time, we also want to minimize the amount of buffering that we have to do to make it reliable. So we've done a couple of things. One of the things that we've done is make these codecs talk to each other. Sure, the green arrows represent audio packets being pushed from one end to the other and from the other end to the near end. The red arrow indicates some metadata, some feedback, as in how you doing? Oh, I'm getting all your packets just fine. Or, hey, you know what? I just dropped 3 packets in a row. Looks like you better start coding at a lower bit rate. I'll have a better chance of getting all the packets. Or I'm going to increase my buffer size to have a better chance of getting all the packets. So we have this two-way metadata communication going on as well as the main audio communication. And again, we call this Agile Connection Technology. IP audio packets are sent. The receivers auto-buffer and reply with status updates twice a second. And the encoder responds, if necessary, by changing the bitrate if it has to. It can even change the algorithm that it's using. We can shift from the AAC algorithm at a higher bitrate down to the HEAAC algorithm at a lower bitrate. The data path here gets fully utilized. Hey, if you want 320 kilobits per second, of AAC between these two sites, if your path supports it, you get it. But if sometime during your broadcast that bit rate becomes unavailable or becomes really challenged because other users are using the same path, well, we'll shift down to a lower bit rate. And latency is minimized because guess what? These AAC algorithms are really good at error concealment. That means they can totally miss a packet or two and cover up where that packet was by using some interpolation in the reconstruction of the audio. This means that you can have 5%, even 10% packet loss, and you don't notice it so much with the audio. And this packet loss gives us the ability to reduce the buffer size to where we actually do miss a packet and then realize, aha, that's the threshold point. Don't need the buffer to be any lower than that. Let's crank it back up a little bit so we don't lose a packet. So we always can have the best latency possible and the best bit rate possible automatically. Now, of course, you can set all this for fixed if you want to. But if you want the automatic functionality, it's there automatically. Now let's talk about characterizing an internet connection. A very important point I want to bring out is that it's perfectly valid because the internet itself is rarely the problem when you have a connection problem. Most often, the problem or the problems come in the last mile or in your router configuration or in the local use of your network. In other words, two of those three things are stuff that you can do something about. The third one, the last mile, you can call and complain. So doing an internet test from a proposed IP audio point, like a remote site, or from your studio or somebody else's studio, doing a test from there to some server on the public internet, that's a pretty valid test, even though it's not end-to-end. And you can do end-to-end test. In fact, that's exactly what the Zip1 does. In fact, let's go back to that slide. Right there, the Zip1 is doing end-to-end testing all the time. Every packet is an end-to-end test. But if you want to pre-select a site, if you want to pre-qualify a site to see how's it going to do IP audio, then doing tests from that site to some server on the public internet is a valid way to check out that site, especially if you do it from each of the two ends to some server, because we think the internet is usually pretty reliable. Okay, so here we have a simple speed test from my office in Nashville, Tennessee. I'm not going very far. I'm going to a server that is somewhere in the Comcast network in Nashville, and I'm getting a download speed of 35 megabits per second and an upload speed of almost 8 megabits per second with a ping time of 19 milliseconds. Not bad. Especially, I remember this particular test was done over Wi-Fi in my office, so you might add a couple of milliseconds or more just for the Wi-Fi transfer. So pretty good test. A speed test doesn't tell you everything, but it does at least get you an idea of, is this going to work well or not? Now, by the way, the audio speed that we're going to be sending on this, okay, minimum of 16 to 20 kilobits per second, maximum of, maybe 300 kilobits per second. Unless you want to send linear audio, that would be a couple of megabits per second. So this connection here at my office looks like it's going to be just fine for whatever I want to do. Here's another test I did a few days later. I did this one in Las Vegas from my hotel room at the NAB with a WiMAX Clearwire mobile modem, and didn't fare so well. I think there was a lot of interference. There may have been a lot of other people using the same site, and it was pretty bad. Download speed of 0.2 megabits per second, or 200 kilobits per second. An upload speed of a little better, half a megabit per second. Ping time, pretty terrible, 124 milliseconds for something local. And hey, the server was about 100 miles away in Mojave, California, but it got a grade of F. Pretty bad on this test. Now, do these speed tests really characterize, though, everything we need to know? The answer is no. They don't characterize everything we need to know. They do give us a rough idea, but they don't tell us everything. Here is a really good test that's going to tell you pretty certainly how well your IP audio is going to work. If you go to the web and look for VoIP test or VoIP jitter test, you're going to be led to a number of different tests that you can do with your browser. And most of them involve using Java. So a lot of browsers nowadays either won't use Java or make it difficult. So you're going to have Java installed on your PC for the more sophisticated tests to get done. And several of these, including this one, this came from a website called whichvoip.com. And I'll provide links for this. Wherever the metadata is for this video, you should be able to find links to this. There's also a link at the Telos website, telos-systems.com. There's a little white paper that I did about these different tests available on the internet. So anyway, let's look at this one. This was pretty good. You see the graph on the left, the jitter scale from -2 to +8 milliseconds. So there's 500 packets showing a worst-case jitter of just over 2 milliseconds. This is with my wired Comcast connection, and you know, this is quite good. Worst-case jitter of 2 milliseconds. Hey, an audio packet, a typical IP audio packet of compressed audio contains 20 milliseconds worth of audio, and there would be 50 packets per second at such a rate. So you're looking at jitter that is, you know, about 10% of the amount of data that a packet has in it. Not bad. I think we could actually do this link with probably 0 buffering, assuming this is worst case, and it may not be, but it was the case for those 500 packets. Now here's another case. This was done using a mobile connection over 4G, and you can see that it's a lot worse, on the order of magnitude, you know, 2 orders of magnitude, not 2, well anyway, an order of magnitude times 2 worse. So we have up to 40 milliseconds of jitter. Well, that would be 2 packets. I mean, 2 audio packets in typical IP audio. So we'd have to have at least 40 milliseconds of buffering at the receive end in order to assure uninterrupted audio. And really, you'd want a lot more than that. You know, I might dial in 200 milliseconds of buffer to take care of worst-case packet jitter. So wired, you can see, definitely better than 4G. Is the 4G manageable? Absolutely. You're just going to have to dial in more delay. Here's another test that can be done. It's round-trip time, or round-trip time consistency. In this particular test, 5 tests are done. Here, this is on the wired connection. It's really good. You can see those blue bars all come pretty close to the average green line. This was over the 4G, though. Not as good. I mean, not unacceptable, but you can see there's a, let's see, a difference in the worst cases there from 80 milliseconds in the quickest round-trip time to about 138 milliseconds. Let's call it 140. So we've got a difference there of 60 milliseconds, a difference in the worst to best round-trip times. So that kind of falls in line with our jitter, doesn't it? That's pretty close to the jitter figure. So you have to figure out your buffering to be at least enough to take care of this difference, the delta, the difference in the round-trip time. And here's a nice graph that typically gets shown when you do a VoIP test. This graph shows that my average jitter on the Comcast was 0.5 milliseconds, and I had 0 packet loss. Good news was I had 0 packet loss on the 4G connection, but I did have an average of 10 milliseconds of jitter, and as we saw, the worst case jitter was about 40 milliseconds. So I think you ought to plan for the worst case jitter. So anyway, we go on to the next result here, and this is kind of a figure of merit, the audit report. On the Comcast connection, I got all green lights for using that connection for voice over IP. And for the 4G connection, 3 green lights, 1 question mark, and that's the jitter. It's higher than what a voice over IP connection would really want to see. All right, next, our second key to great audio over the public internet. Configure and optimize your router. And that would be each router that you possibly have control over. There are really a couple of things that you can do. Let's look at connecting 2 zip1s through the public internet. And there's a router, and there's a router, and there's the internet connections to those routers, and there's the local connections from the routers to your zip1s. Well, if that's all we were doing, fine and dandy. Not a whole lot to optimize here. However, the reason we have a router is to use other gear. So we might easily have other PCs attached to the same router. Now, hey, if you can have your own drop, your own connection, your own internet service provider connection just for your zip1, that is ideal. It's hard to get better than that, and then it just becomes a matter of how much money you spend with your provider and what kind of connection that you get. If, however, you're going to share a connection, and I can't say that we really advise doing that, but in the practical real world, you're going to be sharing your connection, then we're going to have to do some router optimization to try to make things as best that we can. Hey, at the remote site there on the right-hand side, you might well have a laptop doing some things, just like we saw with the Lightning 100 remote at the pizza place. All right, so how do we make this work out well? How do we tell the routers to, first of all, allow things on the internet, like other Zip 1s, to connect to my Zip 1? We do that typically through port forwarding. And the other thing is, how do we tell the routers that, hey, the audio packets from the Zip 1s are important. They need to be handled on an expeditious basis. They need to go first, if at all possible. Well, one thing that we have to do is configure a router. We get better performance from our system if we can configure a port forward, or some routers call it a port mapping. Now, I want to point out that it's entirely possible. In fact, let's go back to the previous graphic. It's entirely possible for two Zip 1s to connect to each other with absolutely no router configuration. And that is done with the aid of the Zip server. The Zip server is run by Telos. It's a free service that Telos offers. And what it is, it's your Zip 1 registering with this server out there. It's right now we have one in the US. We're adding servers in a couple other continents, one in Europe and one in Asia for now. And by registering with the Zip server becomes aware of where your Zip is, where your Zip 1 is. And it also has an established connection now through your firewall. And most firewalls, not all, but most firewalls can then accept connections back through them because the Zip 1 has already said, hey, I'm here. It's okay to send me something. So I'll have a graphic later showing the Zip server involved with this connection. But using that, you actually don't have to configure your routers at all. For configuring the router, though, there is a benefit in doing that. And tell you what, I'm going to pause for a second and show you over here what that benefit is. This is a Zip 1, and I'm going to make a call to the Telos test line. Now, this Zip server is behind a configured router. The one at Telos, though, is not at the moment. It's configured just to do the normal connection. Here, I'll punch that button, and you might be able to see it. The connect light is flashing. It will take 5 to 10 seconds for the Zip server to negotiate with the router at Telos to let this connection come on through. And lo and behold, there it is. We're decoding audio. I'll crank it up there. And this is the audio coming from the Telos test server. So it took about, 5-10 seconds to connect. I'll disconnect right now. Let me connect to another Zip 1, though, that is not behind, or that is behind a router, but the router's been configured for the port to forward through it. And I'll call this Zip 1. I honestly don't know where it is, but I know it connects right away. There, you see that? Connected right away. Okay, so if you want some instant connectivity to your studio site, which you probably do, then best to put a port forward in your router. And let's take a look at doing exactly that. This is in an Apple Airport Extreme router, and I'll give you another example of another router here in a minute. But you can establish a port mapping, as they call it in Apple. In fact, we'll zoom in on this one. Here I've typed in Zip 1 rack, so that's the Zip 1 in my rack room, so that's the friendly name. The ports that you choose to use can be any ports you want, except you want to avoid certain ranges. So every IP address, along with it comes this notion of 65,000 and change ports. And the lower 1,000, maybe the lower 5,000, are set aside for some common uses. You shouldn't use anything below 1,000. Those are all set aside for important stuff. Best to choose something that's actually in a high range. Now, in this particular zip, I happen to choose 2,068. I happen to know that was okay, but normally I choose something really high, like 20,268. But you can choose whatever you want as long as you tell your Zip 1 what the port is and you map the port. So in this case, I mapped both the UDP and the TCP usage ports. And there's my fixed IP address, 192.168.0.68. Now that's my LAN, the internal IP address of that Zip 1 that's in the rack. So when a port request comes in, say from the zip server, to port 2068, then the router will let that packet come right in, and it will send it to the device that's at 192.168.0.68, which is where I've told it to, and it'll send it on to the port there that's 2068. So you can also do port translation with many routers. Let's go ahead and take an example of that here. Here's a port forwarding setup on a Linksys router. We'll zoom in a bit, and you can see that, for example, on this entry here where it says Barracks, that's the friendly name, Barracks, the external port that we selected to use, some high number, fairly random port, 24,780. But the Barracks itself only understands HTTP requests for its web page on port 80. So we translated that external request on that port number of 24,780 to port 80 when it's an inside request. And it's being sent to the Barracks box's internal number of 192.168.1.247. So this is, again, this is where you set up port forwarding. And there's different interfaces to do it. There's actually some great websites on the internet. One of them is portforwarding.com or .net or .org. But there's websites that explain very well how to do port forwarding. For a ZIP1, you want to forward the zip server port to it if you can. If you don't, it's okay. You'll still probably connect. It'll just take a few seconds longer every time that you do it. Another notion to contend with is this idea of quality of service. Now, it's often called QoS, or quality of service, in routers. It's really not QoS. QoS implies end-to-end quality of service. What routers really are capable of is something that you might call packet prioritization. And this is for outbound. This is for uplink from your network to the internet. It's not possible to do packet prioritization in the other direction. We have to take packets as they come in from the internet. But if we want to line up packets in a row to go out our internet connection, then we may give some priority to which ones get to go out first. By the way, this assumes that there's some contention for that. If you're, uploading several things from different computers at the same time, do you want your audio packets to have priority? The answer is yes, you probably do. So in this case, I have enabled the packet prioritization, again, what this router calls QoS. You can set the upstream bandwidth. I've set it to automatic, but you can also set it to whatever you know the upstream bandwidth is. And there are several different ways that you can specify what packets will be prioritized. One way is by the MAC address of the device. So it doesn't matter what IP address that device would be given in a DHCP process. It would only matter what the MAC address is. Well, every ZIP1 has a MAC address, so you could do it that way. However, you don't want to use a ZIP1 in your network on DHCP. You would prefer that it be a static address. That way your port forwarding can work to it. So this probably wouldn't be the way that you'd get that done. There's another way of doing it here, and that is by the actual physical port into which something is plugged in on the back of the router. So in this router, I've set to low priority the first 3 ports, and the 4th port, whatever's plugged in there, its packets get a high priority. Doesn't matter if they're BitTorrent or a phone call or an email, whatever's plugged into port 4. Well, of course, you'd want to make sure that what's plugged into port 4 is your ZIP1. Another way to do it is by the application. In other words, what does the packet involve? What protocols does it involve? In this case, the RTP protocol, because the router inspects every packet anyway, the RTP protocol, or by the port number, gets a higher priority if you want it to. There's some routers also have this notion of clicking to optimize gaming applications. Of course, gamers want to be able to shoot somebody else before they get shot, so you do want packet prioritization for gaming. So there's an overview of packet prioritization. It's going to vary widely from router to router. Some routers aren't capable of it. For a home-style router, any router that is optimized for gaming will probably have these features built into it. And any higher-end router, you'll be able to program packet prioritization. And so now your ZIP1s will have at least upload prioritization ahead of other things. And that helps ensure that your packets that you're sending come out on a regular basis and they're not hindered by the packets from other devices on your network. All right. Let's finally take a look at choosing the appropriate IP codec mode, algorithm, bitrate, and buffer size. Well, we'll jump right into that. The first and simplest mode that any IP codec works in, and they're all compatible this way, is what's called an RTP push mode, where a IP codec is sitting there on the internet with a port forwarded to it, waiting for somebody to push upstream to it. And as soon as it receives a stream, it'll decode that and play it, as long as it's a compatible stream. That is used in situations where you already have good security. Maybe you're on a VPN, maybe you're on a private WAN, and you have guaranteed bandwidth. If guaranteed bandwidth is not a problem, you can just push a stream right to that other ZIP1 or other IP codec. And this is the method in which more codecs are compatible with each other. Again, you don't get lots of good supervision, you just get the ability to push a stream and it decodes at the other end. A good example of a codec that pretty much only does this kind is the brand from Barracks. And there are others as well that have this push mode. Again, no supervision, it just pushes the audio. Now there's another mode that we recently put into this Telos ZIP1. It's called Symmetric RTP. With Symmetric RTP, you have to have that configured to use applications such as Lucy Live Lite and other such similar software apps where there's not a lot of sophistication involved. What happens is you push a stream to the codec, and the codec looks to see where that stream has come from, and it sends a reciprocal stream right back to where the first stream, the incoming stream, came from. Most routers will handle this with no configuration. Sorry, that you got to configure the port forward, but as far as the return stream, it's usually not a problem at all. The router on the other end will just let it come on in because you're sending a stream out through that same port. So it works quite well. Here we go. Simple. It works fine with ample bandwidth. It's unmanaged, so you must underutilize it or over-provision the bandwidth. And typically you're working with a fixed buffer size here. It's not automatically going to adjust. This is what is used with Voice over IP, Lucy Live, and Lucy Live Lite. I should point out that with Voice over IP, RTP push is used after the setup is made. So there's SIP, Session Initiation Protocol, where the two different codecs will talk about, hey, what codecs do you have? Here's what I have. And they'll agree on their port numbers and such, and after that it's a push. With the ZIP1 and with other IP codecs, again, this is the simplest way, and you don't need a SIP or other protocol to make this happen. If you know what the other end's expecting, you can just push it there. All right, let's take a look at how you set up Lucy Live Lite, or what that setup looks like. I won't go through all the details. I do have a video on that also on YouTube and available through our website. So you can set up Lucy Live or Lucy Live Lite this way. There's your phone, your iPhone or your Android phone or your tablet that would be configured with Lucy software, and that will place a push RTP call over through the public internet to a ZIP1. And the ZIP1 would be set up to reciprocate, to send a symmetric RTP stream back the other direction to the Lucy Live software. That way you can hear what's going on. Here's an example of how that would work right here. I can hold this phone up and push this button, and there we go. We connected that quickly. I'm talking in G722 in that direction, sending G722 back to me, and well, there you go. We're on the air. Maybe you can hear that a bit. Normally you'd have a headset plugged into this, and maybe even you'd have an external microphone. In fact, now's a good time to show you this. With Lucy Live or other such software, you can use something like the iRig Pre. Plug this into the top of the phone or wherever the headphone and mic jack is. And now you've got a XLR connection for your professional mic, and you also have a headphone connection right there. And this does this can do the phantom power for the microphone. It also has a mic preamp in it to get the level right. Here's another unit, competing unit from Tascam, the IXZ, does the same thing. And you can just get a plain Jane cable that has no electronics. I think there is a blocking capacitor in this jack. And if this works well for you, fine. Funny thing is, the price of this cable is basically the same as the iRig Pre. They're very close in price, so you might want to get something that has some electronics in it. And moving on here in our diagram, you take this audio and send it to and from your audio console, sending remote audio to the console and hopefully sending mix-minus audio back to the ZIP1 so the person on remote can hear a mix-minus feed. All right, let's look at the next protocol, or the next mode, if you will. RTP mode and symmetric RTP were a couple of initial modes there. They're simple. Here's one that we got to explain a little bit before. We call it TSCP, Telos Session Control Protocol. That's where we have this audio back and forth with agile connection technology. We send metadata back to see how things are going. Do we need a higher bit rate, a lower bit rate, a bigger buffer, a smaller buffer? And that, of course, is a bidirectional connection, and with metadata going in both directions. All right. Let's look also now. I told you how the zip server works, and going to get some more details on that. Here's WRLT Remote 1, and here's the WRLT Studio as example zip ones, and there's the public internet. Well, we're going to assume that we have firewalls here, because basically any business or home does. And the firewalls, of course, the router and firewall in the same box, connect to the public internet. Well, then also on the public internet, Telos has established this thing that we call the zip server. Generically, you might call this a rendezvous server. So these different zip ones check in with the zip server. The zip ones are made aware. They come with the default server programmed in, but you can change that to a different zip server if one becomes available to you. And the zip server basically keeps track of which zip ones are where in terms of their IP address. Also tracks their port numbers too. So now the zip server has this knowledge. It's like a phone directory. It helps these zips that want to call each other get connected. Now, the audio can go through the zip server, but that's not the idea. The idea of the zip server is to tell these two units where they are so that one can call the other with a friendly name, doesn't have to know the IP address of the other. The zip server knows that. But the zip server helps establish this direct connection from one zip one to the other zip one. That's the preferred calling method. That gives you the lowest latency and the least amount of hops in your connection. Of course, that green line really should go through the public internet. It's not really direct like that. But at least it doesn't go through the zip server. So if, however, the firewalls that are involved are too restrictive, then the zip server can and will relay the audio streams for you in both directions. That does involve typically a bit more latency, so that's why we typically try to hand it off to those firewalls. And if you have port forwarding done, we can almost always hand that right off to the firewalls. So making a call through the zip server, or with the help, I should say, of the zip server, the call itself doesn't go through the zip server, it just gets set up by the zip server. That's how this remote got on the air quickly and easily, and with almost no technical knowledge on Josh's part. That's also how this call and remote got set up at KVMR. Now, in this situation where you're doing the full-time STL, you can use the zip server, but you don't have to. And in fact, Dave Anderson and Avery Ditmars here, those zips are set up to call each other with TSCP, the Telos control protocol, but they don't have to use the zip server to do that. They know the IP address of the zip that they want to talk to, the only zip they'll ever be talking to on the other end. So it's not necessary to have that phone directory of different zip servers. All right, so let's take a brief look at coding algorithms and how you might decide which ones to use. We get this question a lot. We'll just review these quickly. You know, G711, well, that is basically the phone codec. That makes your voice sound like a telephone. It's 3 kilohertz of, wonderful audio quality. Actually, if done right, it's reasonably clear sounding, not too unpleasant to listen to, but you don't want to really have music over it. The reason G711 is in the Zip 1 is for compatibility with voice over IP. So if your Zip 1 is registered with a SIP server, and it certainly can be, then you can make a call. You can make a phone call out to a telephone from the Zip 1. And you can also receive a call from another telephone. So that works out pretty well. You can also use G722. That's what software like Lucy Live Lite has in it. One reason G722 is unencumbered by high expense. And so it's easy to incorporate into various codecs and software products. Good quality voice, 7 kilohertz, very low delay for G722. If you're just doing a voice remote, it's fine. It's way better than a phone call. Not as good as any of the other codecs, but it's way better than a phone call. There are some other choices here. You know, the default codec, the one that we just always tend to go to, is this AAC ELD, Enhanced Low Delay. It's part of the AAC family. It sounds great when you consider the low bit rate. It's good for voice or for music up to 64 kilobits per second. It'll go down to about 16 kilobits per second. There's also HE, or high efficiency AAC. That's great for music up to 96 kilobits. So both of these are the highest quality that you're going to get over a bandwidth limited connection. I wouldn't want to use them for a full-time STL, but if you have to, you have to. If you want to use it for contribution audio that is going to be aired once, fine. But if you really want to get the highest quality you can, then you'll want to use an AAC codec like just plain AAC or AAC low delay. And you're going to want to use either of those codecs at 96 kilobits per second or higher. And the AAC and the AAC low delay will both go up to 320 kilobits. There's an optional codec that we're going to make available. It's Enhanced aptX. So if you're an aptX fan, if you like the extremely low delay of aptX, then you can have it with this Enhanced aptX. And here's a list of the bit rates that are supported. Starting at the bottom, Enhanced aptX needs quite a bit of bandwidth, 512 kilobits per second for that to function, but it sounds great. And then you have the AAC codecs from 96 to 320 kilobits, and then the HEAAC or the AAC Enhanced Low Delay. Those are lower bit rates. And then, of course, your G711 and G722, which are both fixed at 64 kilobits per second. If you're just doing a remote, like the remote that we saw from Lightning 100, those are done typically at 64 kilobits with AAC Enhanced Low Delay. If you want to make an STL for full-time audio, you're probably going to want to use AAC. You can use AAC low delay, but if you don't need the lower latency, like for going to a transmitter site, I wouldn't use it. The AAC low delay is not quite as efficient as the full-fledged AAC is. So quite a variety of codecs here. You can experiment and play with, see what the ones that you like are. Of course, the rule of thumb is the higher the bit rate, the better it's going to sound. But don't be afraid. If you have to do a live remote using AAC Enhanced Low Delay at 32 kilobits per second, it's not going to be terrible. It's going to be quite usable on the air, especially for a remote. So if you're challenged by bit rate, don't be afraid to go lower with those newer and better codecs. Well, I hope you've learned something here. There are some links available. Hopefully, wherever you're seeing this video, if it's on YouTube, there'll be some documentation along with it to give you links to other YouTube videos where I explain how to set codecs up, and then also some links to this paper about how to find different websites for testing your connection and seeing whether IP audio is likely to work from your location. Hey, thanks for watching. I'm Kirk Harnack. Appreciate you being here, and good luck.